Good morning, students. In today's class, the topic to be dealt is DIT FFT algorithm. DIT stands for decimation in time. FFT, as we know, it stands for fast Fourier transformation. So this is one of the first of the radix 2 FFT algorithm which will be ourselves getting introduced to. As discussed in the previous class, in this algorithm, the approach used is what is called as divide and conquer approach. So this decimation in time FFT algorithm, it basically involves in breaking up a given n-point transform into two n by 2 point transforms. Once again, each of these two n by 2 point transforms will be again split into two n by 4 point transforms and so on. This breaking up or this decomposition process takes place as long as we are going to end up in 2-point DFTs. That is why we generalize this algorithm as such, saying that a given endpoint DFT is performed using several 2-point DFTs. To begin with, let's consider a given sequence x of n. I assume that the sequence is of length capital N, but note that n should always be a power of 2. What if it is not? If it is not, we can append the required number of zeros to make n as to be a number that belong to power of 2. The first step is whatever is a given length n sequence, that is x of n, is decimated into two sequences of length n by 2. One of that particular sequence is said to be composing of the even indexed values of the given sequence x of n, while the other is said to be consisting of the odd indexed values of a given sequence x of n. We represent them as the sequences as shown below. The first line represents a given sequence starting from indexing 0 till n minus 1. This given sequence is split up into two sequences, one for even indexing and the other for odd indexing. For even indexing sequence, the indexing will start from 0, 2, 4 and so on till where? N minus 2. Note n minus 2 also refers to even index sequencing. For odd index sequencing, the sample values are collected as what? First sample, third sample, fifth sample and so on till where? N minus 1 indexed sample, which is supposed to be an odd value. So we know that given a time domain sequence x of n, we translate the given time domain sequence into its equivalent frequency samples by using the generalized definition of DFT as given by this particular equation. Since my intention is to split up the time domain sequence into two counterparts, one for even and the other for odd, accordingly, the above equation, which is representing the frequency samples, okay, is written as x of k. The whole summation is split up into two individual, one representing the even indexing and the other representing the odd indexing. Please note that within the summation, the term remains the same. The term remains the same. But whereas for the summation indices, there exists a change. For even indexing, the indices run from 0 to n minus 2. For odd indexing, it runs from n is equal to 1 to n minus 1. To modify or to get the result as per the standard format, I introduce a new summation index term called as R. In the first summation, I assume the value of n is equal to 2 times R. And in the second summation, I assume the value of n is equal to 2r plus 1. By incorporating these values in the above equation, the summation indices with respect to r will attain its new value. In the first summation, since the value of n is replaced by 2r, as n tends to 0, r also tends to 0. As n, note that here, what is the upper index? N minus 2. As n tends to n minus 2, r tends to n by 2 minus 1. The steps in detail are been shown over here. Similarly, in the second summation, by replacing n is equal to 2r plus 1, as n tends to 1, r tends to 0. As n tends to n minus 1, r tends to n by 2 minus 1. So now, with this new summation index r, the above equation is rewritten as the first summation, where r is varying from 0 to n by 2 minus 1. Please note that in this term, n is being replaced by 2r. And in the second summation, these are the indices, and the value of n is replaced by 2r plus 1. Here also, the value of n is replaced by 2r plus 1. But in the next step, we just do a small substitution, saying that considering this term, the twiddle factor term, w2 base n 2rk. First, write what is wn as e power minus j 2 pi by n 2rk as it is. I bring this 2 towards the denominator and rewrite this as e power minus j 2 pi divided by n by 2 times rk. In this position, in place of n, it is n by 2. Accordingly, this is representing by twiddle factor w to the power of rk, not just capital N, it is n by 2. If it was n here, this would have been n. Since it is n by 2, here also there exists n by 2. Accordingly, we write the above summation and replace this term w2 base n 2rk by w2 base n by 2rk. Same thing over here. What I've done over here, there are two terms. One is wn into 2rk, that is returned by this term, multiplied by what? Wn into 1k, that is wnk. In the next step, the first summation is been retained as it is. In the second summation, in this whole of this equation, the last term is not consisting of the indices stack r. Hence, it can be treated as constant and it has been pulled outside the summation series. That is what we have done. Next, we are going to generalize the above equation as x of k is equal to the first summation term is abbreviated as g of k, wn to the power of k as it is. The second term is abbreviated as h of k. Note that in this case, k is ranging from 0 to n by 2 minus 1. It is not n minus 1 because we have decomposed the n point DFT into what? 2 n by 2 point DFTs. That's the reason. So what is g of k? It is not n point, but it is n by 2 point DFT of what? Even index samples of my original sequence. What is h of k? N by 2 point DFT of the odd index samples of a given sequence. This is how I represent g of k and h of k. Note that they run from 0 to where? Till n by 2 minus 1. But the point of interest is, for a given sequence x of n, the n point DFT has to cover from where? Starting from 0 till n minus 1. That is, both for g of k and h of k, the term k must run from 0 till n minus 1, But in the above equations, where is the summation running from? 0 to n by 2 minus 1. Why? Because in the next sentence, what we say is, it's found that both g of k and h of k are said to be periodic with a fundamental time period equal to n by 2. That is why for any value of k greater than what? N by 2 minus 1. The next value after n by 2 minus 1 is what? N by 2 minus 1 plus 1. Minus 1 and plus 1 will get cancelled. End up with what? N by 2. This is the next value after n by 2 minus 1. Starting from n by 2 till n minus 1. Since the above two sequences are periodic in nature, they take the same value as of 0 to n by 2 minus 1. That is, n by 2k value is equivalent to 0, n by 2 plus 1 is equivalent to 1, and so on, and so on. This is acquired based on what property? Periodicity property. That is why to compute the n-point DFT of n, the equations to be generalized are x of k is given by this particular equation for what? K running between 0 to n by 2 minus 1. But whereas for k running from n by 2 to n minus 1, this is the equation. And note that, for example, if I could substitute the first value of k as what? N by 2. N by 2 minus n by 2. It is what? G of 0. Again, over here is what? Substituting k as n by 2. It is what? H of 0. So the first value of n by 2 is equivalent to what? This value of 0 in this equation. Based on what property? Periodicity property. So after the first stage of decomposition, the flow, this is called as the flow diagram. The flow diagram looks like this, What exactly you must understand from this particular flow diagram is that, so what is my given point DFT here? The given point DFT x of k is what? N point DFT. So what is the first stage of decomposition? Decompose or decimate or split the given n point DFT to what? N by 2 point DFT. I'll repeat once again. The given DFT, n point DFT, is split up into what? 2 TWO2 n by 2 point DFTs. And these are those two n by 2 point DFTs. For the first n by 2 DFT, what are the inputs? All even index samples. For the second n by 2 point DFT, for the methodology, what are the inputs? Odd index samples. What is the output of this DFT? G of k series. What is the output of this particular DFT? H of k series. Now, say for example, in this case, what is x of 0? X of 0 is equal to G of 0, this line, G of 0. At this point, where is other input coming from? The other input is coming from where? From H of 0. So G of 0 plus what? I must multiply this middle factor, Wn to the power of 0 times H of 0. Similarly, what is x of 1? G of 1 plus Wn to the power of 1 multiplied by what term? H of 1. What is x of 2? X of 2 is G of 2 plus Wn to the power of 2 multiplied by what? H of 2. Similarly, we are going to get all the values starting from x of 0 till where? X of n minus 1. At this point, what you must appreciate is the given n point DFT is split up into two n by 2 point DFTs. For the first DFT structure, we are inputting the even index samples. For the second DFT structure, we are inputting the odd index samples. G of k represents the what? DFT of the n by 2 DFT of the even index samples. H of k is what? Representing the n by 2 point DFT of what? Odd index samples. The outputs G of k and H of k is been combined along with the Studel factors. See, I've shown this one dotted line. the dotted line is representing what is called as combining algebra. Combining algebra. It's called as endpoint combining algebra, because what exactly I'm doing over here, yeah? I'm trying to add two terms. One term is what? For example, what is x of 0? G of 0 plus what? Plus not simply h of 0, g of 0 plus wn of 0 multiplied to h of 0. G of 0 plus wn of 0 into h of 0 is x of 0. Since I'm trying to add up these two terms with one multiplicative term, since a bit of mathematics has been employed over here, it is called as combining algebra. It is called as endpoint combining algebra because I'm doing this for how many terms? For all the n terms, starting from 0 till n minus 1, I'm doing this n times. N times I'm using this algebraic operation. Hence the name endpoint combining algebra. Now, the point of interest is, at this point of time, how many complex multiplications are involved? See, we generally what is that, try to measure the computational efficiency based on multiplication rather than addition. Addition also matters to a small extent, but what it matters to a greater extent is the number of complex multiplications. That is why I've stressed more about the complex multiplications. At the end of this topic, we'll discuss both complex multiplications as well as additions. Time being, the total number of complex multiplications required to evaluate the endpoint transform after the first stage of decimation is given by, this is a formula, a variable. Eta 1 is equal to n by 2 whole square plus n by 2 whole square plus n. From where did I get this? Very simple. Get back to this structure. See, for any given endpoint DFT, what are all the total, how many number of complex multiplications are involved? We're learning this in the previous two classes. How many? N square. For endpoint DFT, it is n square. For n by 2 point DFT, how many complex multiplications do we require? N by 2 whole square. So 1 n by 2 whole square for this, 1 n by 2 whole square for this. And as I told you, we're using this endpoint combined algebra. See, h of 0 is multiplied with wn of 0. H of 1 is multiplied with wn to the power of 1. H of 2 is multiplied with wn to the power of 2. Again, n times I'm doing this multiplication where in the combining algebra. That is why the total number of complex multiplications is what? N by 2 whole square for the first half DFT, n by 2 whole square for the second half DFT, and n for what? The n complex multiplications in the combining algebra. If I could simplify this, after first stage, the total number of complex multiplications is equal to how much? N square 2 plus n. N square by 2 plus n. Continuing further with the decimation. What did I say? The decimation process has to be continued until and unless I end up with what? 2-point DF test. So what is the next stage? Each of the two n by 2 point sequences are further what? Decomposed or decimated into two more sequences. Now what is the sequence length? N by 4. N by 4. So now say for example, this is what x of n, the original sequence. What was the range of n? Starting from 0 till n minus 1. What did we consider the first stage? Decomposing a given sequence into what? Even indexed and odd indexed. For even indexed, what did I use the abbreviation? 2r. For odd indexed, 2r plus 1. Time being, I'm considering only the even indexed. That is what? X of 2r. So what does x of 2r looks like? 0, x of 0, x of 2, x of 4 till where? N minus 2. In this case, what is the range of r? 0 to n by 2 minus 1. Now, I introduce a new variable called g. I abbreviate x of 2r as what? A new variable g of r. Okay. So in my x of 2r, what all samples value I had? All the even index samples, 0, 2, 4, and so on. When I represent this in terms of a new variable g of r, g of 0, 1, 2, and so on, what is g of 0? It corresponds to x of 0. What is g of 1? It corresponds to x of 2. What is g of 2? 4. What is g of 3? X of 6, and so on. And what is g of n by 2 minus 1 sample? X of n minus 2 sample. Now, what I do is, again, since g of r is what? Basically, n by 2, n by 2. So what I want to do is, that n by 2 point DFT has to be split up into two, what? N by 4 DFTs. Again, what? Even indexing and odd indexing. What are samples of even indexing? 0, 2, 4, and so on. Till where? Please note this term. It is not n minus 2, but it is n by 2 minus 2. Because right now we are in the n by 2 point DFT stage. We are decimating a given n by 2 point DFT to what? To n by 4 DFTs. That is why the last term is n by 2 minus 2. This corresponds to what? Indexing. Original sequence, x of 0. What is g of 2? X of 4. What's the next term? If it is what? If it is g of 3. Can you guys say what will be g of 3? The last term, x of, it should be x of 7, and so on. So what about the odd indexing samples? G of 1, G of 3, G of 5, and so on. Till where? Since it is odd indexing, it is n by 2 minus 1. G of 1 corresponds to x of 2. G of 3 corresponds to x of 6. And so on. Till where? Till x of n minus 2. And please note that in this case, the n by 4 DFT's computation, L ranges from 0 to n by 4 minus 1. Since we know that DFT of g of r corresponds to g of k. What is g of r? The even index sequence of my original input x of. So what is g of k? Summation index r varying from 0 to, since it is n by 2 point DFT, it is n by 2 minus 1. The sequence g of r multiplied by its two-diddle factor, and note this is n by 2 point DFT, hence here it is n by 2. Again, this is what? Split up into two terms. What is that? One for even indexing, the first one. The second one is what? For the odd indexing. Like how we are done in the first step here. Split up into even index and odd index. What did we do in the first step? Replace n by 2r. Replace n by 2r plus 1. Same thing, we are introducing a new term called as L. In the first indexing, replace r by 2l. In the second indexing, replace r by 2l plus 1. I think again I will not say more. It's all about mathematics. You people must understand, appreciate it. Any doubt, get back. So what happens to the new summation indices? It varies from L is equal to 0 to n by 4 minus 1. Replace r by 2l, replace r by 2l. Same thing over here. These are the indices. R is what? Replaced by 2l plus 1 and 2l plus 1. Please note that again when you bring this 2 to the denominator, it becomes WNLK by 4. Same thing, this 2 bring it to the denominator, it is WN by 4LK. And the term WN by 2 to power K is a constant which has been pulled outside the summation, It is exactly the same as the previous one. There it was n by 2 computation. Here it is n by 4 DFT computation. There I had the term R. Here I am having the term L. Now, this above equation can be rewritten in terms of the new variables A of k and B of k. What is A of k? The DFT of the above sequence for even indexing sample. What is B of k? The DFT for the odd indexing sample. Please note that in this case, k varies from 0 to n by 4 minus 1. But what I'm actually interested with, before that, what are A of k and B of k? N by 2 point transforms. And they are said to be what? Periodic with a fundamental time period equal to n by 4. N by 4. Since I'm interested throughout the range from 0 to n by 2 minus 1. If you ask, madam, why not n minus 1? Right now, I'm not in n point DFT. I've decomposed my n by 2 point DFT to 2n by 4 DFTs. That is why the upper limit is what? N by 2 minus 1. K and B of k are periodic with period n by 4. Note that for k ranging between 0 to n by 4 minus 1, this is the equation. And for k ranging between n by 4 to n by 2 minus 1, this is the equation. Like how we have done for g of k, representing it in terms of A of k and B of k, following the same procedure for h of k. In the exam also, if they ask this derivation, there is no need to show all the steps for h of k. Show only for g of k and write it as similarly for h of k and just deduce the final, write the final equation. So h of k is what? Written in terms of C and D. C of k and D of k very much similar to the above expressions. For k ranging between 0 to n by 4 minus 1, this is the expansion. For k ranging between n by 4 to n by 2 minus 1, this is the expression. Now, after the second stage of decomposition, okay, this is how the flow diagram looks like. Let me just tilt it, okay? Rotate once again. Yes. Now see, okay, very simple. For understood the first flow diagram. What is the first stage? What is the first basically? See the given n by 2, the given n point DFT, okay? The n point DFT has to be split into what? 2n by 2 point DFTs. The next stage, each of these n by 2 point DFTs has to be split into what? 2n by 4 point DFTs. Again, this n by 2 point DFT is split up into what? 2n by 4 point DFTs. So again, if you could go for the next stage, what is going to happen? This n by 4 point DFT has to be what? Split into 2n by 8. This into 2n by 8 and so on. Till where we go on decimating? Till I end up in 2 point DFTs. So for the first n by 4 DFTs, these are the inputs. For the second structure, the inputs, so on for third and the fourth structure. The output of this is A of k, this is B, this is C, and this is D. To combine A and B, to get what? G of k, I'm using one n by 2 point combining algebra. To combine C and D to get h of k, I'm using one more n by 2 point combining algebra. But what am I interested with? X of k. What is x of k in terms of G and H? To combine G of k with H of k with its middle factor, I use one more n point combining algebra. Okay, this is how we do it. Now, at this stage, what are all the total number of complex multiplications involved? See, for this, no, okay, but I think I'll show from this diagram only. Okay, I'll just once rotate it. Give me a small pause. See here, I told you, since it is, if you could visualize this block, the total number of complex multiplications involved in this one n by 4 point DFT is n by 4 whole square. 1 n by 4 whole square, 2 n by 4 whole square, 3 and 4. Totally how many? 4 n by 4 whole square plus how many n by 2 combining algebra I've got? 2n by 2 combining algebra. I have to add this also. How many n-point combining algebra I've got? Single one. So take this n into consideration. So accordingly, the total number of complex multiplications are 4 times of n by 4 whole square plus 2 times of n by 2 plus n. This is for the 4 individual n by 4 DF tests. This is for 2 n by 2 combining algebra, and this is for 1 n-point combining algebra. If I could combine all those things, I end up in n square by 4 plus 2n complex multiplications at the end of second stage. The overall theorem says that, the algorithm says that this decimation process continues on and on till I reach where? 2-point DFTs. And it has been proved mathematically that the total number of stages required, how many stages we require, that will be equal to the value v given by log n to base 2. Okay. For example, if they say, compute an 8-point DFT, how many stages I require? If you could write it as v is equal to log to base 2, the value of n is 8. Log 8 to base 2, I end up in 3. So how many stages basically? 3 stages. So whatever point DFT they say, use this formula to figure out what? The total number of stages of decomposition required. And it has been proven that once I get the number of stages, how many complex multiplications will be involved? That is given by n times of log n to base 2 stages. Because for every stage, how many stages are there? Log n to base 2. So for every such stage, I require so many complex multiplication. Yes or no? If it was an n-point DFT, I require what? N into n. If it is what? N by 2-point DFT, I require what? N into n, or say n by 2 whole square, and so on. Accordingly, the total number of complex multiplications required would be equal to n multiplied by the number of stages. That number of stages is given by log n to base 2. Log n to base 2. So we can verify that by using this DIT-FFT algorithm, the total number of complex multiplications has been reduced by from n square to n times log n to base 2. To just take a small example, say for if it is an 8-point DFT, if I'm going for direct computations, the total number of complex multiplications is equal to how many? 8 square is what? 8 8s are 64. 64 complex multiplications. But whereas if I could come over here, earlier log 8 to base 2 will be what? 3. 3 multiplied by 8 is what? 24. Just compare. Where is 64 and where is 24? Don't you think that the complex multiplications has got reduced from 64 to what? 24. That is the advantage of V using this GIT algorithm. So generally I've shown over here in general that n-point decomposition can be structured like this. The first stage, whatever is a given n-point DFT, it has to be what? Divided into 2 n by 2-point DFTs. Then what? Each of this n by 2 should be divided into what? 2 n by 4 DFTs. Again this n by 2 to 2 n by 4 DFTs. Then take this n by 4, split up into what? 2 n by 8 DFTs, and so on. This also, and this also. This procedure goes on and on till where? Till I end up in only 2-point DFTs. My DFT should have only what? 2 inputs and 2 outputs. Till I get this 2-point DFT, the whole process continues on and on. Now, okay, see here, I'll just show the last diagram, 1 second. I've just shown the signal flow diagram for an 8-point DFT. See, what is that? This is the final 8-point DFT here. You see what I have to do? See, what is 8 by 2? 8 by 2 is what? 4-point DFT. Then what is again that 8 by, first was n by 2. So 8 by 2 is 4. Again that n by 4 is what? 8 by 4 is what? This 2-point DFTs. So the whole flow diagram is said to be consisting of 3 stages: n, n by 2 and n by 4. So what is 8 by 4 is 2. That is what? A 2-point DFT. So as I told you, for example, see this is what one such structure. 1, 2, 1. What is that? 2-point DFT. One more 2-point DFT. One more 2-point DFT, and so on and so on. How exactly we must write this butterfly structure, and how do the inputs appear and how do the outputs appear? Let's just look into it. Please note that in this case of this decimation in time FFT algorithm, always the inputs will appear in the bit reversed order, but whereas the output will appear in the regular order. So what do you mean by that? I'll do one thing. Yeah, better. How exactly we would write this structure, and what are all the findings? What exactly we can assist from this particular diagram? Let us pick this in the regular class on Tuesday. Okay. Fine. Please go through this derivation completely. Any doubts, get back to me on Tuesday's class with all your doubts. Have a nice day. Take care.